Every program you run has to remember things, numbers, names, scores, images. But where does all that data actually live, and how does the computer find it again in an instant? To really understand data structures, we first have to understand memory itself.
So where does all of this memory actually live? Inside your computer sits a small chip, and packed onto it are billions of microscopic cells laid out in a giant grid. Each cell is nothing more than a tiny switch paired with a bucket that can hold a little bit of electric charge. If the bucket is charged, we call that a 1. If it's empty, that's a 0. That single 1 or 0 is a bit, the smallest piece of information a computer can keep. To store your data, the chip simply flips the right switches on or off. To read it back, it checks which buckets are charged. And because every cell sits at its own row and column, that position becomes its address, so the computer can jump straight to any bit in an instant. Billions of these little switches, flicking on and off, are what hold every photo, message, and app on your device.
Picture your computer's memory as a huge street of identical boxes, lined up one after another. Each box holds a small piece of data, and each one has its own unique numbered address. When the processor needs a value, it doesn't go searching. It jumps straight to the address. Give it the address, and it reads or writes that exact box in a single step. Let's zoom inside one of these boxes. Each box holds a single byte, and a byte is just 8 tiny switches called bits. Each switch can only be on or off a 1 or a 0. With 8 switches, you can make 256 different patterns, so one box can store a number from 0 up to 255. But what about bigger numbers? Simple, the computer just lines up more boxes together. A whole number, the kind we usually call an int, takes up 4 boxes side by side. That's 32 switches in total. And this is the secret behind something you saw earlier. When we stepped through the array, the addresses jumped by 4 each time, because each number quietly fills 4 boxes, not 1. But a single value is rarely enough. Suppose we want to store the test scores of a whole class. If we just scatter them randomly across memory, we'd have no way to find the 10th score without checking box after box. We need a system, an agreed way to organize data so we can both store it and get it back quickly. That system is called a data structure. The simplest data structure is the array. It places all of its items in one continuous block of memory, back to back. Because the boxes are the same size and evenly spaced, the computer can find any item with a tiny calculation. Take the start address and add the index times the item size. That means reading element 500 is just as fast as reading the first. Instant access by index. Let's watch this in real code. We loop an index I starting from 0. Each time we read the ith element, the computer turns it into a single address, the base, plus I times the item size, and jumps straight to that cell. As I moves on by 1, every access costs exactly 1 step. Because the values sit side by side, walking an array is fast and completely predictable. Until now, every box has held a plain value like the number 42. But a box can also hold something cleverer, an address. A box that holds an address is called a pointer. Think of it as a sticky note. It doesn't contain the thing you want. It tells you exactly which box to go and look in. There are 2 little symbols for working with pointers. The ampersand, written before a variable, means, what is this box's address? And the star, written before a pointer, means, go to the box this points to and use whatever is inside. So if P holds the address of X, then star P gives you back the value of X. And here is the key idea: a pointer is just a value too. It lives in its own box, and on a modern computer it takes 8 bytes, big enough to name any address in memory. But arrays have a cost. Their size is fixed, and inserting in the middle means shifting everything else over to make room. A linked list solves this differently. Each item, called a node, stores its value plus the address of the next node. The nodes can live anywhere in memory, joined together by these pointers. Now inserting is cheap, you just rewire a link. The trade-off is access. To reach the 5th item, you have to follow the chain from the start, 1 node at a time. Now the same loop for a linked list. We start with a pointer P pointing at the head node. Each turn we read the node's value, then follow P to its next pointer, hopping to wherever the next node happens to live. There's no index formula here. To reach the 5th node, we must pass through every node before it, same goal, but a very different journey through memory. When we say one structure is faster than another, what we really mean is this: how does the work grow as the data grows? Computer scientists capture that with big O notation. Reaching any item in an array is a single jump, no matter how big the array gets. We call that O of 1 constant time. but watch what happens if we insert a value into the middle of an array. There is no spare gap, so every item after it must shuffle one place to the right to make room. With 100 items, that's up to 100 moves. With 1,000,000 items, 1,000,000 moves. The work grows in step with the size, we call that O of n. A linked list is the mirror image. Adding a node is just rewiring a single link, but reaching the nth node means following n links, one after another. So neither one is simply better. Each is fast at some jobs and slow at others. Before we allocate anything, it helps to know that a program's memory is split into regions, and two of them matter most. First, the stack. This is where local variables and function calls live. It's automatic and orderly. Every time you call a function, a new frame is stacked on top, and the moment it returns, that frame is thrown away last in, first out, just like a stack of plates. It's fast but short-lived, and its size must be known in advance. Second, the heap. This is one big shared pool of memory you can dip into whenever you like. You ask for space with malloc, and it stays yours until you give it back with free. The heap is flexible and can hold data that outlives any single function, but you have to manage it yourself. So local variables live on the stack, while things like our linked list nodes live on the heap. So where do these scattered nodes actually come from? While your program runs, it has a big pool of spare memory called the heap. When you want a new node, you call malloc and ask for just enough bytes to hold one. Malloc finds a free block in the heap and hands you back its address, a number that says where the block lives. You keep that address in a pointer. Ask for a second node, and malloc gives you another free block, but wherever there happens to be space, often far from the first. That is why linked list nodes end up scattered, and why each one must store the address of the next. A pointer, really, is nothing more than a variable that holds an address. But Big O still isn't the whole story. Inside a real computer, the processor is extraordinarily fast, while the main memory is comparatively far away and slow. So the processor keeps a tiny, lightning-quick notepad right beside it, called the cache. Here's the trick. Whenever it fetches one box from memory, it doesn't grab only that box. It scoops up the whole neighborhood around it in a single trip, betting that you'll want the neighbors next. For an array, that bet pays off perfectly. The neighbors are the very next elements, so one trip to memory serves many reads. For a linked list, the nodes are scattered all over, so the neighbors are usually useless, and the processor is forced to make a fresh, slow trip for every single node. This is why, even when the Big O looks identical, walking an array can be many times faster in practice than chasing a linked list through memory. So let's pull it all together. Memory is just an enormous row of numbered boxes where each box holds 1 byte, 8 bits on or off. The processor can reach any box instantly as long as it knows the address. Data structures are simply the ways we arrange data inside this space. An array packs its items side by side, so you get instant access by index, and the hardware's cache makes scanning it beautifully fast, but its size is fixed, and inserting means shifting. A linked list scatters its items and threads them together with pointers, so it grows and shrinks with ease, but reaching an item means following the chain, and the scattering hurts cache speed. And underneath it all sits the divide between the stack, where local variables come and go automatically, and the heap, where data you request with malloc lives until you free it. There is no single best structure, only the right one for your data, your operations, and the machine you are running on.